so let's speak about the osmotic pressure. So this is that pressure that I was alluding to earlier. So because water wants to move according to its gradient, this creates a pull or a force, okay? Anytime we have the ability or the propensity of particles to move, that is described as a force or a pressure. And that's how we get the osmotic force or the osmotic pressure. So it's a reflection of the solute concentrations, right? So again, looking at this example here, we have high solute concentration on side 2 and low solute concentration on side 1. So we have a water gradient, right? Water wants to move from side 1 to side 2. So we can then express that movement in terms of this force. And we can consider that force the pressure that it would take to stop the water from flowing. And that would be a reflection of the force, the magnitude of the force that wants to push water from side 1 to side 2. Okay? So if you look at the relative solute concentrations, we have 300 milliosmoles on side 1, 500 milliosmoles on side 2, and that gives us a differential water concentration of 55.2 versus 55.1. So we can then describe different osmotic pressures. Okay, so there's 7.4 atmospheres, which just represents the force that water wants to stay on this side, and 12.3 atmospheres, which is the force with which water wants to move to this side. And so now we can speak about an osmotic pressure gradient, right? So because of the different concentrations of solute and the different concentrations of water and the different concentrations of osmotic pressure, we can then describe the osmotic pressure gradient, where there's a higher osmotic pressure on side 2 and a lower osmotic pressure on side 1. So water will move from side 1 to side 2. Okay, so the big picture here is that the osmotic pressure is the force with which water wants to move, and we can consider that force the pressure that would be required to stop that movement of water. All right. We can then speak about tonicity. So tonicity is slightly different from osmolarity, and they're often confused. Tonicity is basically the osmolarity, but we're only looking at impermeant solutes. So solutes that cannot move across the membrane. When we speak about osmolarity, we're not really interested in whether or not the solutes can move. All we're interested in is the relative concentrations. But tonicity goes a step further, and it is only taking into account the solutes that cannot move across water. So we have a water gradient based upon different solutes, but we're only considering the solutes that are impermeant to the membrane in question. So we can then describe a isotonic solution, which has an osmolarity of 300 milliosmoles, a hypotonic solution, which has less of an osmolarity, and then a hypertonic solution has a greater osmolarity, right? More solutes that are impermeable that are in that solution. Okay, so here's a good example to kind of differentiate between osmolarity and tonicity. So in these two concentrations, in this scenario, in this illustration, we have solutes which are impermeant in purple. They are inside the cell, and impermeant just means that they cannot move across this membrane. We have urea, which is a permeant solute, so urea can actually move across this membrane. So whereas in osmolarity, we would look at urea, when we talk about tonicity, we're going to completely ignore urea. Okay, so the solution on the left can be said, can be described as being isoosmotic, meaning that we have the same number of particles dissolved inside, 300 milliosmoles, as we have outside, right? Also 300 milliosmoles. But on the right, when we speak about tonicity, we're going to completely ignore urea. Because urea can move into the cell, tonicity does not take urea into account. And so if we're just considering the impermeant solutes, we have a high concentration inside and zero concentration outside. So we then have a water gradient, which makes this a hypo or hypertonic solution. Will this be hypo or hypertonic? So we know it's isoosmotic, but in terms of the tonicity, is it hyper or hypotonic? hyper, so we're completely ignoring urea. So look at that image on the right and just pretend you don't see the solutes in yellow. All you see is the solutes in purple. What will that make our solution outside the cell? Would it be less of a tonicity or more of a tonicity? It would be less, right? So if you're considering that there is no urea here, there would be no particles outside the cell. So we'd have particles inside and no particles outside. So we would have a high water concentration outside and a low water concentration inside. And so this ends up being a hypotonic solution, okay? And so this is how we can see that osmolarity is different from tonicity. We can have an isoosmotic solution also be a hypotonic solution. Okay, any questions on that? Any questions on that? Okay, so here is a table that kind of just summarizes these differences. I won't go into detail with this table, but if you don't understand the difference between osmolarity and tonicity, I would advise you to kind of go through this table in a little bit more detail and really describe those differences. All right, so on this slide are two examples that highlight what we just spoke about and highlight the movement